Hello and welcome to Metaphor Math again. Today we'll be solving problem 2a in Maxwell Rosenlicht's Intro to Analysis. So again, we're doing set equality here. So like before, there's two steps to showing set equality. We have to show that the left side is a subset of the right side, so that the complement of A is a subset of A, and A is a subset of, so let me put, this is our first step, and our second step is to show that A is a subset of the complement of A. So starting with 1, to show that the complement of A is a subset of A, we have to show that any arbitrary x, if it lies in the complement of A, then it must be also in A. So let x be in the complement of A. And this is the first key point here. I'm going to write it in a different color, maybe blue. So if x is in the complement of any set x, this is just the general case. If x is in the complement of any set x, then x is not in x. And that's just the definition of the complement. The complement of a set is any set, the complement of some set x is everything that's not the set x. So if x is in the complement of x, then it cannot possibly be in x by definition. So if x, let me switch back to pink here, if x is in the complement of A, then x is not in the complement of A. And this leads us to our second point. If x is in the universal set S, so here's our universal set X, and then here is our set that we care about A, and of course our set A could be the empty set. It doesn't specify here, but let's just draw it as a non-empty set here, and that's A, and then the universal set is S. If X is in S, let me write it in blue again, then there's two cases. Either x is in A or x is not in A. So one of these must hold true. So back to our problem. Let me box this here for importance. So if x is not in the complement of A, then that means that let's kind of consider, okay, so what if, suppose x is not in A. So let's suppose this right side case here. If x is not in A, then remember by this definition here, then that means that x is in the complement of A. And I should have said up here, this is actually the if and only if statement. X is in the complement of A if and only if. Sorry about that. And so that means, so if x is not in A, then that means that x is in the complement of A. But we already know that we just showed that x is not in the complement of A. Thus, so I'll say, but this is impossible. And since there's only two possibilities, x can either not be in A or be in A. Thus, x is in A. So we showed any we showed that if X is in the complement of the complement A, then that implies that, let me write that in a different color because we just finished showing it, that, well actually I won't write that up there. Thus X is in A, I'll just say it. If X is, so we just showed that if X is in the complement of the complement A, that it must also be in A, showing 1, that X, the complement of the complement of A, is a subset of A. Now all we have to do is show the other direction. Change colors again here. If, so now, we're showing part 2 here, let X be an A, then this means if X is an A, then X cannot possibly be, X is not in the complement of A, and what we go back to here, remember an if and only if statement means that if X is in the complement of A, then X is in X. Oh, I'm sorry, I said that wrong. Let me say that again. If X is in the complement of X, then X is not in X. And if X is not in X, then X must be in the complement of X. So this big set X is a set. So if X is not in the complement of A, then X must be in the complement of the complement of A. The complement of this set, which is just the complement of the complement of A. Which implies that A is a subset of the complement of the complement of A. Because we just showed that if X lies in A, then it must also lie in the complement of the complement of A. So, and that means we're finished. We just showed that they're subsets. The two sets that we care about on the left and right side of the equal sign are subsets of each other.